a warm welcome. This is the third video of the evaluation of residues at poles. In the previous videos, we evaluated residues at poles of order 1 and 2. In this video, we will evaluate residues at poles of order greater than 2. In such situations, we have to apply the result. If A is a pole of order n, residue of f at A is equal to 1 by n minus 1 factorial, limit z tends to a, n minus 1th derivative of z minus a the whole raised to n f is z. If A is a pole of order 3, then you have to take n equal to 3 in the result. Similarly, if A is a pole of order 4, then you have to take n equal to 4 in the result, and so on. Let me start. Consider the function z raised to z by z minus 1 the whole cube. Clearly, its pole is 1 with order 3. We notice the equation for finding residue at single poles and double poles. Here you have to apply the equation of calculating residue when its order is 3. For that, you remember the German formula for finding the residue of a function at a pole if its order is n. And its equation is, if A is a pole of order n of a function f, then residue at A of the function f is 1 by n minus 1 factorial. Here A is a pole of order n, then in the equation 1 by n minus 1 factorial, limit z tends to a, n minus 1th derivative of z minus a the whole raised to n into f is z. That is, the equation is 1 by n minus 1 factorial, limit z tends to a, n minus 1th derivative of z minus a the whole raised to n f is z. See, in this function, here n equal to 3. So you put n equal to 3 in this equation. Residue of f at A is equal to, here n equal to 3. So 1 by 2 factorial, limit z tends to a, second derivative of z minus a the whole cube into f is z. Here you find the second derivative of this function, then you take its limit. Here A is equal to 1. So 1 by 2 factorial, limit z tends to 1. Second derivative of z minus 1 the whole cube, f is z is z e raised to z by z minus 1 the whole cube. You make the simplification here. So it is 1 by 2 factorial, limit z tends to 1, second derivative of z e raised to z. So you differentiate z e raised to z twice. Its first derivative is, here it's a product, so you apply product rule, and product rule is uv dash is first into derivative of second plus second into derivative of first. First into derivative of e raised to z is e raised to z itself plus e raised to z into derivative of z, it is 1. So it is z e raised to z plus e raised to z. Next, its second derivative is, you differentiate this term. Here the first term is a product, again you apply product rule, that is first into derivative of second plus second into derivative of first plus derivative of e raised to z is e raised to z itself. So z e raised to z plus here 2 e raised to z. So this is the second derivative of z e raised to z. So it is 1 by 2 factorial, limit z tends to 1, z e raised to z plus 2 e raised to z. Here you put z equal to 1. So 1 by 2, it is e plus 2e. That is 3e by 2. Next, consider the function 1 minus e raised to 2z by z raised to 4. Clearly, its pole is 0 and its order is 4. So, for finding its residue, in this equation, you have to keep n equal to 3. So, residue of f at 0 equal to 1 by 3 factorial. Here n equal to 4. Here, since it is 4, you write here 3 factorial. Limit z tends to 0. Third derivative of z raised to 4 into f is z. That is 3 factorial is 6. Limit z tends to 0. Third derivative of z raised to 4 into 1 minus e raised to 2z by z raised to 4. That is 1 by 6. Limit z tends to 0. Third derivative of 1 minus e raised to 2z. Its first derivative is minus 2 e raised to 2z. See, derivative of e raised to x is e raised to x. Derivative of e raised to ax is a e raised to ax. Its second derivative is minus 4 e raised to 2z. Its third derivative, we have to find its derivative up to 3. It is minus 8 e raised to 2z. It is 1 by 6. Limit z tends to 0. Minus 8 e raised to 2z. You put z equal to 0. So e raised to 2z become e raised to 0. E raised to 0 is 1. Any quantity raised to 0 is 1 except for 0. That is a raised to 0 equal to 1. For a not equal to 0. If a equal to 0, 0 raised to 0. It is an indeterminate form. That is, it is not determinate. So here it is 1. So 1 by 6 into minus 8. That is minus 4 by 3. Really, in this question, you can easily find its residue by writing its Lorentz series expansion. For writing its Lorentz series expansion, you have to express e raised to 2z in the form of an infinite series. We know the expansion of e raised to z. What is e raised to z? E raised to z is 1 plus z by 1 factorial plus z square by 2 factorial plus etc. By using this result, you express e raised to 2z in the form of an infinite series. That is 1 minus 1 plus 2z by 1 factorial plus 2z square by 2 factorial plus 2z the whole cube by 3 factorial plus etc. Whole divided by z raised to 4. It is 1 minus 2z minus 4z square by 2 factorial minus etc. Whole divided by z raised to 4. It is minus 2z minus 4z square by 2 factorial minus etc. divided by z raised to 4. That is minus 2 by z cube minus 2 by z square minus. By using Lorentz series expansion, we can find the residue at a singular point A by considering the coefficient of 1 by z minus a in the Lorentz series expansion of f z. Really, the coefficient of 1 by z minus a is our b1. So here you have to write the coefficient of 1 by z. So for getting the coefficient of 1 by z, you have to write the next term. Here the next term is 2z the whole raised to cube by 3. So minus 8z cube by 3 factorial divided by this is raised to 4 minus etc. That is minus 2 by z cube minus 2 by z square minus 8 by 6 1 by z minus etc. See, this is the Lorentz series expansion of the given function. See here, residue of f at 0 is coefficient of 1 by z. Coefficient of 1 by z is minus 8 by 6, that is minus 4 by 3. This is the another way of finding residue from its Lorentz series expansion. Also, you keep in your mind, you can easily find the residue from the Lorentz series expansion if the given function contains exponential function or trigonometric functions. In that situation, you can depend on this method. Let me try to answer one more question. So consider the function sin 2z by z raised to 6. Clearly here, 0 is a pole of order 6. So you have to take n equal to 6. Residue of f at 0 equal to 1 by 5 factorial, limit z tends to 0, fifth derivative of z raised to 6 into fz. That is 1 by 5 factorial, limit z tends to 0, fifth derivative of, if you put fz equal to sin 2z by z raised to 6, you can see z raised to 6 will cancel each other and the remaining function is sin 2z. Here you have to find the fifth derivative of sin 2z. What is the first derivative of sin 2z? It is 2 cos 2z. We know derivative of sin ax is a cos ax and derivative of cos ax is minus a sin ax. Derivative of second derivative of sin 2z is minus 4 sin 2z. Third derivative is minus 8 cos 2z. Its fourth derivative is 16 sin 2z. Its fifth derivative is 32 cos 2z. So here you have to write 32 cos 2z. Here you put z equal to 0. Then you can see cos 0, which is 1. So answer is 1 by 5 factorial into 32. That is 32 by 120. Here also you can find its residue by writing its Lorentz series expansion. You keep in your mind, if the function contains exponential function or trigonometric functions, then you can easily find the residue by expressing its Lorentz series expansion. We know sin z is z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus etc. Similarly, you also keep in your mind cos z is 1 minus z square by 2 factorial plus z raised to 4 by 4 factorial minus etc. With the help of this series, you can see it is 2z minus 2z the whole cube by 3 factorial plus 2z the whole raised to 5 by 5 factorial minus etc. the whole divided by z raised to 6. Really, if A is a singular point, then residue of f at A is coefficient of 1 by z minus a in the Lorentz series expansion of fz. So here residue of f at 0 is coefficient of 1 by z in the Lorentz series expansion. See, this is its Lorentz series expansion. So you collect the coefficient of 1 by z, which is the residue of the function at 0. For that, you consider 2z minus 2 cube is z cube by 3 factorial plus 2 raised to 5 by 5 factorial into z raised to 5 minus etc. The whole divided by z raised to 6. You have to find the coefficient of 1 by z. So from here you will get the coefficient of 1 by z. So you write up to that term, and this is 2 by z raised to 5 minus 2 cube by 3 factorial is z raised to 3 plus 2 raised to 5 by 5 factorial into z minus etc. The coefficient of 1 by z is the residue of f at 0, and it is 2 raised to 5 by 5 factorial. See, the both answers are unique. So you keep in your mind, if the given function contains trigonometric functions or exponential functions, you can easily find corresponding residue from its Lorentz series expansion. In this, you have to keep the basic results of e raised to z, sin z, cos z in the form of an infinite series. That results are, see, these are the results. E raised to z is 1 plus z square by 2 factorial plus etc. You can find these series expansions by using Maclaurin series, which you have studied in your 4th module.